1 over 8 times 8, right? And also we have 1 over 2 times in total 6. So we'll have 4. Okay. And the next one, so it's a p-type or n-type? N-type, yes. So this is the p-type, okay? So because this Fermi level is above EI, right? Fermi level is above EI, so it's definitely an n-type semiconductor. And is there a hole drift current? Yeah. Yes. Yes. Why? So basically, we have this, this EC is kind of tilted, right? This is tilted, so it means there must be electric field. Okay, so there must be a hole drift current. Okay, right? So this should be 4, and this is force, right? And this is 2. Okay, right? So let's move on to the new topic. So actually, let's just review. So actually, this slide actually tells you the how to answer question 2, right? Problem 2 in the quiz. So basically, you think about if for the drift current, what's the driving force, right? The driving force is electric field, right? And the electric field is related to the temperature gradient in this electrostatic potential V, and this V is also related to this slope in EC. Right? So if you see this EC or EI or EV, they are tilted, there must be a electric field inside the material. And also you can tell this EC is defined as this minus QV plus EC. This is EC naught. This is any reference value. So you can see if we apply the positive voltage, it can pulse down the band. So this side tilted down because we applied a positive voltage here. Okay, and there's several ways to determine the electric field direction. So one way is to look at this slope, right? So you can see the electric field is related to the slope of EC, right? So the dEC over dx is slope. So and if we look at if this EC is tilted like this, then it means this is negative value, right? So this is negative slope, and it means the electric field is along the this negative x direction. Okay, and of course, if this is tilted in the opposite way, then the electric field will be pointing to the right. Right, and this one way, just look at the slope, and another way is to use the water analogies. So this is we have discussed before, and so we have this electron, right? So electrons are like this, water in like in a bottle, right? If we tilt this bottle like this, then the electron will move, right? And these electrons, basically electrons like sinks, right? Move down, right? And then for holes, right, they are like these bubbles in almost full bottle, right? If you tilt this like this, then this bubbles will flow, right? This is moving direction for holes. So this, and also we can use this water analogy to understand the electric field direction. Okay, so the electric field direction or the drift current direction will be the same as the whole moving direction. Right? So you can see if we, for this case, right, if we tilt like this way, then holes are moving to the right, right? Holes are moving to the right. Okay, and which means that the drift current direction is pointing to the right, and the electric field direction is pointing to the right. Okay, and also we discussed the these potential and kinetic energies in this in this band diagram, and you should be able to determine these values, right? So the potential energy is just EC or EV. Okay, and basically you draw a vertical line and draw a horizontal line, find this corresponding EC value. And for example, in this B, just draw a vertical line here, and then draw a horizontal line, and you can find the corresponding value for EC. Okay, and this is potential energy, and for the kinetic energy, it's just difference from this, the actual position of electron and EC. Okay, basically this distance here is a kinetic energy. So we should be able to determine these values, right? And for holes, it's opposite, right? So you need to define a different opposite x-axis. So basically, the whole energy increases when it's moving down. Okay, so that's why this is 0 and this is 1. Okay, and then we discussed another type of current, which is diffusion current. So for diffusion current, we can see the driving force is this gradient in carrier concentration, right? So if the carrier concentration is not uniform, then there must be a diffusion current. So to understand the direction of diffusion current, first we need to know that for this diffusion process, right? It applies for both electrons and holes, so or other particles, right? So the diffusion direction is always from high concentration to the low concentration. Right? So you can see here, if we have more electrons on the left side, then the electrons will diffuse towards the right side. Okay, so this is the electron diffusion direction. And now, because the electron is negative charge, right, the corresponding current will along the opposite direction. Okay, so this is for electron. And for holes, and if we have similar, concentration profile, right? So the holes will diffuse from high concentration to low concentration, which is diffused towards the right. And because holes are positive charge, right, the corresponding current will along the same direction. Okay. So these are the diffusion current. So if we have both drift and diffusion, which means that if we have both electric field and gradient in carrier concentration, then the total current will be the sum of these two contributions. And of course, the total current will be the electron contribution plus the hole contribution. Okay, right? So here's one thing I want to emphasize: the drift current is always in the direction of electric field. Right? So you can see these two expressions are similar, right? And this drift current direction is determined by the electric field. But for the diffusion current, they have opposite sign. Right? So for electron, it's plus, and for hole, it's minus. So although if we have electron and holes, if they are diffused along the same direction, then the corresponding diffusion current for electron and holes, they must along the opposite direction. Okay, And also we discussed the Fermi level in equilibrium, right? So if the system is in equilibrium, then the Fermi level must be a constant. It does not change with position. Okay, so then we can draw this horizontal line for the equilibrium case.
I got a question.
Yes.
So if you dope one side of a semiconductor, the diffusion current would make the whole like. So if I dope one side p-type, and then don't do anything to the other side, over time the whole thing will become p-type.
It's kind of different. So it's related to diffusion, right? So it diffuse, and also it depends on the temperature. What's the diffusion length, right? If the diffusion length is long enough, we give this system enough long time, right? Then the sample will be homogeneous. It will diffuse to the other side.
So it's kind of like heat transfer.
Yes, heat transfer. Yeah. But we will discuss that later. There's some diffusion length scale. Right. And also we discussed the Einstein relationship, and this basically the diffusion coefficient and the mobility, which are these two quantities in these the drift and diffusion current terms. They are they are related to each other. So if we know one of this one value, then we can determine the value for another parameter. Right. And now I also would like to help you a little bit about the homework problem. So I think one homework problem is to try to calculate the average time between collisions. Okay, and to calculate this value, you need to use this microscopic expression for mobility. Right, so mobility is proportional to regulation time tau, or the average time between collisions. Okay, and this is the term we want to calculate. So basically, we want to determine the mobility, right? Because we know the dope level, and the effective mass is what we have already shown you in I think in some lecture slides, right? So we have the effective mass for gallium arsenide, and also this should be the electron effective mass. Okay. And to determine the mobility, we just use the this figure in lecture 6. Okay, and basically we want to find the doping level here from 10 to the 15th and the corresponding mobility. And we know the mobility decreases with increasing carrier concentration. So we try to use this figure and find this mobility is around 8,000. Okay, so we just plug in the mobility effective mass, and then we can determine this top easily. Okay, and another question is about the slope. Okay, so this is basically the this carrier density. Okay, so this is a carrier density profile for two different materials, and so we have this kind of the solid line and a dashed line. Okay, so we want to determine which one has larger diffusion currents, and to do this we just need to use the right equation, right? And this is the right equation. The diffusion here is related to this slope, right? So dp over dx is slope in this carrier density plot. Okay, so basically we want to check which configuration, which distribution can lead to a large dp over dx. Okay, so I have these numbers also labeled here. So then it's very easy to calculate the slope, right? You can see this, the slope is here, and the slope value is like here. Okay, so you can see which one can lead to a large diffusion current, the solid line or the dashed line. Solid line, yeah, because it has a higher slope. And okay, right? Okay, so now let's continue to discuss the new topic. And so we have introduced the intrinsic material, right? For intrinsic semiconductors, we have used this M naught, right, or P naught, and they are same, and it equals this intrinsic characterization. This subscript, this 0 indicates the equilibrium characterization. Okay, and now if we look at this Venn diagram, so there exists a constant process of this these two this process, like we have this recombination and generation. Okay, so for generation, it means that basically we can some electrons in valence band absorb certain energy, so it can jump to the conduction band. So this can create electron hole pairs, or EHP. Okay. And we also have this reverse process. So basically, the electron in the conduction band can go back to the valence band. So this electron and hole can combine, and then it can release certain energy. Okay, so in real materials, these two processes are always happens. So we have both can exist. So now let's try to quantify these processes. Okay, so we have recombination rate. So this is it's proportional to the product of the electron and hole density. So we can use this symbol, this R sub I. So this represents recombination rate. So it's related to the electron and hole density. So it's P naught and N naught. Okay. And for example, if there are lots of electrons but no holes, then this non-recombination can take place, because electron must combine with the hole. Right? Then this recombination rate will be 0. Okay, in this extreme case. So we can define basically a proportionality constant, this alpha sub r. So and this we can write this recombination rate as this alpha sub r and not P naught. Okay, so this is recombination rate, and in equilibrium, everything is balanced, right? So there will be no net change in this N naught and P naught, and the recombination rate must equal the generation rate. So we can define this generation rate as G sub I. Okay, so this G, the generation rate, is the same as the recombination rate. And for the recombination rate, we can write this as Ni squared. Why? Because this, remember the PM product, right? For PM product, this P, N times P is Ni squared, right? So then this recombination rate and generation rate is alpha Ni squared. And this G, because it's called thermal generation, because it's at constant temperature, right? This process here, the generation process here, is activated by the thermal energy. So let's think about what happens if we shine light on a semiconductor. Right? If we shine light on a semiconductor, because the energy of photons can be larger than the band gap. Okay, so these photons can be absorbed by electrons in the valence band, and then this electron can gain enough energy to jump across this band and basically into the conduction band. Okay, so basically this light can create excess electron hole pairs, and for these excess electron and holes, we use this delta N. Okay, so we have delta N and delta P. So these are the excess electron and hole which are created by this light. So at time equals to 0, then let's just shut off the light. If we shut off the light, what can happen? These excess electron and hole pairs will start to recombining to each other. And then if we give some time, then the system will reach the equilibrium value. Okay, so basically this delta N and delta P will go to 0. Okay?
Is this how photovoltaics work?
Yes, exactly. So I will discuss that later. Yeah. So now, what's the time dependence of this delta N and delta P? So let's try to understand how does these excess carriers change with time. So we know eventually this delta N delta P will go to 0. How does this this delta N delta P decays? Okay, so basically, if we look at the band diagram, right? So if we turn off the light, then this electron will go back, and they will combine with a hole in the valence band, and this can release certain energy, right? So this after this recombination, we can either emit certain light, or give off heat. So basically, this energy can be goes into the material and heat the material. Okay. All right. So to understand the temperature dependence of delta N and delta P, we can use this define this certain notation. So this N is basically the carrier concentration, the total carrier concentration, right, for electrons, and it's a function of time. So basically, we would like to have this equilibrium value, right? And because we have this excess carrier, so they just add this excess carrier. And the equilibrium value is a constant, but this excess carriers is time dependent. Okay, and this is for electron, and we can do the same thing for holes. Right? So here we are interested in the rate of change of N. So this rate of change of N, so it depends on basically two processes, right? Two competing processes as we discussed before. So we have the generation, right, and also recombination. So the total, the change of rate, this rate of change is basically the generation rate minus recombination rate. Okay, for generation rate, as we as I showed you before, it's defined as G sub I, right? So it's generation rate, and recombination, right? For recombination, it's rated to this is certain constant, and it's rated to the actual electron and hole concentration, right? Okay, so we are trying to understand how does this change. Try to solve this equation. Okay, so then we can determine this this delta n and delta p. Okay, so to solve this equation, we just need to start with this one, and we know this the actual carrier concentration, right, as function of time. These two equations. So we just plug in. So let me just draw some. So here we have this n, right? So we just replace this n by this equation, and we have p here, right? P just replace this by this equation, right? And for the generation, we know this generation is is given by this equation, right? So this is what we have defined before, right? So this is the thermal generation rate. Is alpha Ni squared. Okay, and for recombination, we just plug in this value for N and P for this expression. Right? So now you can see that if we, for this case, right, this generation is constant. So it's the generation rate is due to the thermal process. And if we, the temperature, if the temperature is the same, the generation rate will keep the same. And for the recombination, actually it changes with time. Because for recombination, it's related to the actual electron and hole concentration. Because this N and P, they are, higher than the equilibrium value. Right? So we have this equilibrium value, but we have some additional term here. Okay, so this n times p is larger than Ni squared. Okay, so this recombination rate will be larger than the generation rate. Okay, right? So from this one, we can just start to plug in, just replace these two, right, by these two expressions. Okay, so this n is n naught plus delta n, and p is p naught plus delta p. Okay, then we can expand this term like this. Okay, so this is after expansion. Expand this last term, we can get 4 terms here. Right? So we can try to simplify this expression. Okay, so for this one, we will see some terms can cancel out, right? So what's n naught p naught? What's n naught times p naught? What's p product? Right? Ni squared, exactly. So this is Ni squared. So we can say these two cancel out, right? And also, let's assume this delta n, right? This delta n is much smaller than this p, or than n, and delta p is much smaller than this p now. So then this is high order term, right? So this high order term will be negligible as compared to other terms. So we also ignore this high order term. Okay? So now this expression here can be simplified like this. Okay? And of course here we also replace this dn over dt by d delta n over dt. And because this basically this N naught is not a function of time, right? It's a constant. So this dn over dt, basically it's the same as d delta n over dt, right? And then we can get this expression here. So it's basically we only have two terms left, right? And we can factor out this alpha sub r. So we have alpha sub r n naught plus p naught times delta n. Okay, so for this one, we can define this term. So this term here, define this term alpha n naught plus p naught as this 1 over tau. Yes, do you have any question? Okay. Right. So this will define this. Basically, it's this tau is a recombination lifetime. Okay, so it's tau n and tau p for electron and hole. Okay, so now for this we can write as one, negative 1 over tau delta n. Okay, so this basically this term here represents this just how this this excess carriers decays, right? So this basically due to the recombination. And also you notice that this for electron and holes, this recombination lifetime are basically the same, and also their recombination rate are same. Okay, this is because every time because we always basically recombine this electron and hole, because we always either create electron hole pair or annihilate electron hole pair. Right? So that's why this electron and hole recombination rate is the same. Okay. Right. So with that, we can understand how does this excess carrier change with time. Okay. So if we turn on the light, we will generate excess electron and hole pairs. So this this electron delta n will be the same as delta p. Now, if we turn off the light, this delta n, this excess carriers will decay, and this decay rate is related to a certain constant. This is recombination lifetime. Okay, and if you look at this equation here, so this is the first order differential equation, and basically we just this try to find the expression for n as a function of time t. Okay, and we can solve this equation easily. So we can get this delta n equals this delta n at time equal to 0. So this is the initial value. Okay, so this is the delta t at the moment when we turn off the light. Okay, then we'll have additional exponential term. This exponential minus t over this t tau sum n. Okay, and this will be this delta n will be same as delta p. Right. So from this equation, we will see that this excess carriers decays exponentially with time, and with a lifetime of this from the time this tau n or tau p. Okay, and for tau n and tau p, the lifetime of electrons is around microseconds. Okay, 10 to the negative 6 seconds. Right. So basically, this is the temperature dependence for this excess carrier. Now we can also plot this, right? Plot this excess carriers as a function of time. So if we plot this, so if this is time, and this is at with delta n, right? So if you plot this as function of time, you will see at time equal to 0, there will be some initial value, right? This is the delta n at time equal to 0. Okay, so this is the moment we turn off light, and then these excess carriers will decay exponentially. So eventually it will go to 0. Okay, so we'll see something like this. Right, so this is how does this delta n change with time. So now, how do we determine this initial value? How do we determine the delta n at time equal to 0? So to do that, we need to define some other terms. So let's first look at this steady state case. Okay. So if we shine a light continuously on a semiconductor, and then we can reach this so-called steady state case. Right? So for steady, what do you mean? What does this steady state mean? It's not equilibrium. Okay? These are different. So for steady state, it's the system reaches basically a constant state. Right? Basically, it means that the systems do not change with time. Okay, right? So then, this the recombination rate must equal the generation rate. So these two should be the same two rates, because this carrier concentration are not changing, right? So if this R is not same as G, then the carrier concentration will either increase or decrease. Okay, right? So now we can define an optical generation rate. Optical generation rate is G opt, and this so if we have this G equal to R, then we can look at this the generation rate and the recombination rate. So here we have two contributions for this generation rate. Okay. So we have this G sub I. So what's G sub I? Yes. Yes, exactly. Thermal generation. So this is what we have defined in the beginning, right? So this is thermal generation rate, because we have this thermal energy, right? Thermal energy can create these electrical pairs with this thermal activated process, and because we also have this illumination, right? So we have additional term. So this G sub OP. So this G sub OP is the optical generation rate. Okay, and this these two will be balanced by this recombination. And recombination again is related to certain constant, and this will be also times electron concentration and hole concentration. Right? So this is the recombination rate. And for the thermal generation rate, because we are at the same temperature, and so this G sub I is alpha Ni squared. Okay, so we can replace Gi by this alpha Ni squared, and this recombination, basically we have N replace N by N naught plus delta N, and P by P naught plus delta P. Okay, so the purpose for this, is try to find an expression for this G of the optical generation rate. Okay, right? So you can see if there's no light, right? If without light, this the generation rate, this due to thermal generation, will be same as a recombination, right? Which is equals alpha R and I squared. Okay. Right? But here you will see this, we have optical generation, and that's why we have this excess carrier. Okay. And so for if we start with this equation here, basically we would like to just expand this, right? If we expand this, we will have 4 terms. Okay, so we have these terms, and also we notice that this delta n should be same as delta p, so that's why we can get this equation here. Okay, so for this equation, again we can, as we discussed before, we can, because this delta n, they are second order term, right? They are small as compared to this equilibrium term, so we can ignore this higher order term. Okay, and also we can see these 2 terms cancel out, right? So then we found it's we can write down the expression for this optical generation rate easily, right? So we'll see that this optical generation rate basically will be alpha m naught plus p naught times delta n. And also, recall that we have already defined this term, right? So for this alpha times m naught plus p naught, remember we have defined this here, right? So this term is 1 over tau. Okay. So we can write down the expression for optical generation rate easily. So basically it's delta n over tau. So this is optical generation rate. And with that, we can determine the initial value. So what's the value here? Okay, so basically with this equation, we can calculate delta n and delta p, right? So basically it's the G optical generation rate times this tau. So this is a boundary condition for time equal to 0. Okay, and usually, this optical generation rate will be a material's property, right? It's a constant for certain material, and also tau. This recombination lifetime is also a material's constant property. So if we know these 2, you can calculate delta n and delta p easily. All right. Okay. So this is basically the steady state carrier concentration under illumination. So we can first determine this delta n and delta p if we know this optical generation rate and recombination lifetime. Okay, and if we know these 2, we can calculate these excess carriers. So we can determine the actual concentration easily. So this actual concentration is basically the equilibrium concentration plus this excess term, right? So this equilibrium is given, so just want to calculate this excess term. Then we can get the actual carrier concentration. And this, this will be the same for both electron and hole. And also notice that this excess electron concentration is the same as this excess hole concentration. right? So, okay, so now I just want to show you just one example. So we have this, we know the optic generation rate, and we know the electron and hole concentration. And again, this N naught and P naught represent equilibrium, right? Equilibrium carrier concentration. Okay, and here basically we have this electron concentration is much higher than the hole concentration, so it's basically it's N-type, right? And it's a silicon, so we can use this PN product to determine the hole concentration. And also we know the recombination at 10 tau. Let's try to calculate the steady state or the actual carrier concentration under this elimination. Okay. So to do that, what's the first step? So what's the equation we need to use? Right? So basically we want to use this equation, right? Right? So we want to use these equations. So what's the first step? So we basically want to use the equation, right? The first equation, right? So we want to use the first equation to determine this delta N and delta P, right? So because we already know this G, right? G and tau, then these two can be determined easily. Okay, so we have this delta N and delta P is basically optical generation rate times recombination lifetime, and we will get this back. And so for this calculation, just make sure you convert these two into the same unit. And use second. All right. So these are the excess carriers. So for the steady state carrier concentration, it is basically the equilibrium plus the excess term. Right? So we can do this for electrons and do this for holes. Okay. But now we can compare these values with the equilibrium value. Right? So for example, we can see the electron concentration. Right? The electron concentration is almost the same as this equilibrium value. Right? It's only changed by 20%. Oh, sorry, 2%. Okay, only increased by 2%. But if you look at the hole concentration, for hole concentration, you can see this delta P is much larger than this P naught, right? So this hole concentration is basically determined by this delta P. So it's several orders magnitude higher than the equilibrium hole concentration. Okay, right? So for this, right? So for these, two different, carrier concentrations, we can determine, we can define this majority carriers and minority carriers. Okay. So for majority carriers, basically it means, either electron in an N-type region or a hole in a P-type region. Okay. For minority carriers, it means an electron in a P-type region or a hole in an N-type region. Okay, and here you can see this is an N-type semiconductor, right? N-type semiconductor. So the majority carriers are electrons, right? And the minority carriers are holes. Okay, you can do this. Or you can define the majority carriers and minority carriers. Okay, and also in this case, we can calculate the NP product. So this NP product, this is the this N times P is this value under illumination. So if we calculate this N times P, it is basically this N naught times delta P. So you can see this N naught times delta P. So this will be 2 times 10 to the 26, right? Because this is 14th and this is 12. You can see this MP N times P is much larger than Ni squared. Ni squared is around 10 to the 20s. So this NP N times P is much larger than Ni squared. So we just want to know that in this case, right? In this case, this NP product or this NP equals Ni squared is no longer valid. Okay, and because this is in non-equilibrium. Okay, and this NP equals Ni squared only is only valid for equilibrium case. Okay. So now let me remind you what is equilibrium, right? So equilibrium here, it means that a condition of no external excitation except for temperature and no net motion of charge. Okay, and examples include like one, if we have one sample at constant temperature and also in dark with no field applied, and so usually we use this subscript this 0 to indicate some equilibrium parameters. So here, especially we want to emphasize this in dark. Why we want to say this in the dark? Yes.
Is the light to change the period?
Yes, exactly. So basically, this light is also external excitation. So basically, we want to get rid of this external excitation. So that's why we want to place this sample in the dark. Okay? And for steady state, it refers to a non-equilibrium condition in which all processes are constant and are balanced by opposing processes. Okay, so by example, we have a sample with constant current or a constant optical generation rate, okay, of electron pairs. So just this generation rate is balanced by recombination. Okay, so this is kind of a steady state. So here, if you look at this example, so it is a steady state condition. So it's in steady state condition, but not in equilibrium, because we have this light, right? It's under illumination. So if it's under illumination, it's no longer in equilibrium. Okay, and or if there's a magnetic field or electric field, then the sample is no longer in equilibrium. Right? So any questions about this this example? Okay, all right, good. So if you want to go back to these equations, so here we mentioned that this delta n is a positive value, right? In some cases, this delta n can be a negative value. So it means that this this x carry can be removed in the beginning. So sometimes I would like to ask you to calculate this delta n, right? So this is also very easy. If you calculate delta n, just use this equation, right? So you just need to find what's the actual chemical concentration and what's the equilibrium concentration. Right? then you can get data and easy. So this sometimes this can be a negative value. Right. Okay. Right. So now we can discuss this photoconductivity, right? We're going to mention this. So this light can create excess carriers, which can increase the conductivity, and this can give rise to a photocurrent. So this is called photoconductivity. And you can just use this equation we have derived before to find the value for this photoconductivity. So this is the current, right? So it's related to the carrier concentration, mobility, and also related to the electric field, right? And we can also write, so this part, right? So this whole part is the conductivity signal, right? So now we would like to determine the increase of this conductivity due to this illumination, right? So basically we have this carrier concentration increase, right? So we have this equilibrium value plus this excess value, right? So for both electron and holes. So then we can determine the conductivity increase as compared to the equilibrium value. For equilibrium, we only have this M naught and P naught. Right? For if we shine a light, we have this excess delta and delta P. So that this conductivity increase is related to this excess carrier. And again, you can see this basically we are creating electron hole pairs. So delta M is always the same as delta P. Okay, so this is conductivity increase. So now if we look at this the current, right? So the current due to this light illumination is basically the conductivity increase times the electric field. Okay, here this is the basically equations for this photoconductivity. Okay, as you can see, if we basically apply shine a light, you get additional current. Okay, and this is very useful. We can use this this properties to make certain applications, right? So we can use this to make a photon detector. So based on the current, we can determine the photon. And also the solar cell is also based on this principle. Okay. Right. Any questions about this photoconductivity? Right. So basically, the principle is very straightforward. We when we shine a light on a semiconductor, it can increase the electron and hole concentration. And we know the conductivity is related to the electron and hole concentration. Right? So basically this can increase the conductivity and increase the current. Okay? Right? Right, so now let's move on to the last topic. And this is continuity equation. So for this continuity equations, it's very useful because we can use these continuity equations to go back to solve all these equations we have discussed so far. Okay. So we can use these continuity equations to understand these this steady state case, equilibrium case. So for this continuity equation, basically we want to understand in this material in certain region, in a small region, in a unique cross-sectional area, how does this electron or hole change their concentration? So basically, we want to understand whether this how does this carrier concentration changes with time within this this gray region. Okay, so basically we want to define this the partial p over partial t, and within this thickness is this delta x. So how does this characterization change? Right. So this change of carrier concentration can be affected by several things. So, for example, if we can have this current, right? So we have current flow and flow in and flow out. So current, what's current? The current is basically the moving charge, right? So let's assume this we have this holes, right? So the holes are moving here. If we have holes moving, this will lead to the current, right? And this basically we have these holes move in and holes move out, right? So we have this current at x, and this is current at x plus delta x. Okay, so basically this is the electron. So here this is basically it can increase the electron, right? If we keep throwing holes into this region, then we can increase the hole concentration. But in the meantime, we have current flows out. So this can reduce the hole concentration, right? So the net change is basically the difference, right? So we have current flows in and flows out, and if there's if these two are the same, then the whole concentration is not changed by this current. Okay, but there are still some other mechanisms. So the change of whole concentration is also rated for them this one. So what's the last term here? It's GOP. What's GOP? Yes.
Optical generation.
Yes. So this is optical generation rate. Yeah. Good. And so basically, optical generation can increase the whole concentration. Right? So that's why we have this this plus sign. Okay. And what's this middle term here? What's the middle term? Recombination. Yes. Exactly. So this is a recombination. So this is a recombination. So basically, this electron and holes will recombine, and this can decrease the carrier concentration. Okay. So that's why we have this minus sign. Right. So to summarize this equation, right? So within this shaded box, so the time rate of change of the hole density equals what is flowing in, right, minus what is flowing out, minus what is recombining, plus what is being optically generated. Right? So all these can change the hole density. Okay? And if we just consider all these contributions, then we can determine the time rate of change of this whole density. Okay, so this is the equation we want to start with. So now, for this equation, we can divide. So we have this delta x, right? So we would like to remove this delta x. So we can divide by this delta x on both sides. So we can remove this, right? So we can remove this delta x here, and delta x here. And here we have this divided by delta x. Okay. So now, if this delta x is very small, then this term is basically this partial j over this partial x. Okay, and also this will be a minus sign. Alright, so this is the continuity equation for holes. Okay, so we will use this equation for solving a lot of to solve the electron and hole concentration. So this is the continuity for holes, and we can do the same thing. We can determine the continuity equations for electrons. Okay, and again, let's start with this equation here, and we can get this too. Okay, so you can see there's some difference here for these two charge carriers. So for electrons, there's no minus sign. For holes, we have one minus sign. Right, so these are the difference. Right, so any question about this continuity equations? So we will show you more. Show you basically you don't need to. Of course, it's important for you to understand this this process, but you don't need to know how to derive this. But you just need to know how we can use these continuity equations to solve certain problems. And I will discuss this in the next lecture. Okay? Alright. So to summarize, we have discussed this steady state carrier concentrations under elimination. So we can create these excess carriers is related to the optical generation rate and recombination lifetime. Okay. And we can determine these excess carriers and also understand how does this excess carrier change with time if we turn off the light. And also this, we also introduce photoconductivity, and this is related to the this change of this carrier concentration. And these are two general continuity equations for electrons and holes, and we will use these two equations, and also we'll try to simplify these equations for different conditions. We'll discuss it in the next lecture. Alright, so that's all for today, and I will see you